Welcome everyone to another geoscience tutorial. Today I will show a simple end-to-end workflow for mineral prospectivity mapping in a Jupyter notebook. If you're into mineral exploration, machine learning, or just want to see how real-world data gets turned into targets, you are in the right place. So the goal here is to turn geology, geophysics, and geochemistry into a probability map of high priority cells. Okay, this is what we're going to do step by step. So set up the notebook and define the safe feature lists to avoid label leakage. Build a balanced training table by pairing positives with sampled negatives. Pre-processing is the next step. Impute missing values, stabilize skews, scale and encode geology. Then the time for quick EDA sanity checks and a two-dimensional PCA view to confirm usable signals. Test and score a few models on whole.split to pick a winner. Time for train the model, train the chosen model on the full balance set and save it. Score the full grid to get per cell probability. Visualize results at low, medium, and high. And finally export the clean CSV for GIS. And optionally, you can rank features to see what drives the model. What you'll achieve is a reproducible notebook that goes from raw features to a ranked prospectivity map, a saved model you can reuse on new areas or community-specific labels, and a simple way to tune selectivity so the high band matches your budget. We model per cell probability of mineralization. So our data, our features are geochemistry, geophysics, and geology, radiometrics, gravity, magnetic, seismics, lake geochemistry, basic geology categories. Our target is a binary label that marks known mineralization cells versus background. So the label here is a training class, and we exclude all other training fields. What we are doing is to lock down clean feature lists and a single pre-processing pipeline. All training except the target are excluded. Numeric get imputed, stabilized, and scaled. Geology is one-hot encoded, and this guarantees the exact same transformed at train and predict time. So by doing this, we won't have any leakage because label helpless columns are excluded from features. Also, missing, skew, and outliers handled consistently. And it's a solid single pre-processing that can plugs into any model pipelines. So training and predictions use the exact same pre-processing. So this is the code. First, imports. I load the tools I need: NumPy, Pandas for arrays and tables, scikit-learn pieces, imputers, scalars, transformers, pipelines, and column transformers. Next stage is about constants and passes. I declared what file to read and which columns are special. For example, data paths, here is CSV location. Target calls is the label we predict, the binaries 0 and 1. Meta calls is IDs and coordinates never used as features. Cat calls is geology text columns, which is optional. Then we load the data, or read the CSV into data frame. Then we define feature list safely to prevent leakage by removing any training helper columns from features. Here we have leak calls, which is all columns starting with training. Feature columns, feed calls, everything except meta, target, and leaks. And we split features into numeric versus categorical for different pre-processing. Next is numeric transformers. I built a reusable numeric pipeline, 4 steps: impute, fill missing values with the median, log1p that tame heavy-tailed variables and guard negatives by clipping to 0 first. Quantile transformers map each feature to an approximately normal distribution, robust to outliers. Standard scalar, center to mean 0 and standard deviation 1, helps many models. Next stage is categorical transformers. It's optional. I encode geology text to numbers safely. Impute most important categories. Then one-hot encoder turns categories into binary columns and ignores unknowns at prediction time. Next is combined per column logics. I apply numeric setups to numeric columns and categorical steps to geology columns in one object. Anything else is dropped. And 8 is quick confirmation. I print row count and how many features of each type the model will see. We isolate all positives, then randomly sample the same number of negatives. This 50-50 table forces the model to learn the positive pattern instead of defaulting to background. We shuffle rows and confirm counts are equal before training. This is the code. We set the target here. We predict training class. 1 means positive, 0 means background. Split the table here by pose, keeps all positives rows, keeps the rest as candidate negatives. We count positives by n underline pose, len pose stores how many positives exist. This drives balancing. And to balance the classes, underline pool sample randomly picks the same number of negatives as positives. And the reason that, as far as I'm concerned, a 50-50 set stops the model from winning by always guessing negatives. So random status is 42. That makes the sample reproducible. Next step is concatenate and shuffle. So stacks positives over negatives, shuffles all rows, cleans the index, and the result is a balanced randomized training table. Step 6 is to verify and balance. Shows class counts. I expect 1, 1, 50-50, and then we print rows and columns. So this is important because mineral positives are rare. Without balancing, the model learns to ignore the positives. So a 50-50 set forces the model to learn what makes positives special. If you dislike dropping negatives, use class weights later. But for fast benchmarking, this downsample is simple and effective. Then I run a fast health check. I quantify missing data, glance at a few histograms, then project to a two-dimensional with PCA after robust transforms. I'm not chasing perfection here, just verifying the data looks sane and there is some class structure before modeling. So this is the code block for basic stats, for example, which columns have missing value. So x underline num here, take only the numeric features columns from the balanced training table. The copy here makes a safe working copy, so I don't alter the train data frame. In the next line, describe computes summary stats per columns. I add first 15th and 99th percentile to see tails and the median. T flips rows and columns, so each row is a feature. I keep the most useful fields. Count helps us to know how many non-missing value, means standard deviation, average, and show the average and spread. Maximum, minimum shows us extremes. 150, 99, as far as I'm concerned, is lower tails, median, upper tail. So the next line, we have is an A, so marks missing cells as true or false. Mean on Booleans gives a fraction missing per column. Stored descending to see worst offender first. And finally, we print 10 most missing columns, preview the first 10 feature summaries. So high NA rate here means that the imputation matters. Consider adding missingness indicators. Large gap between 99% and maximum means outliers. We need to use log or Winsorise. If standard deviation is much more larger than greater than mean and minimum, far below 1%, this means that heavy skew and we need to transform. Low count relative to rows means weak coverage. We need to consider dropping or treating very carefully. So the results here for us is that we have missing data about 11.8 in radiometrics case, potassium, thorium, and uranium. Others 0%. So imputer will handle this. Now we can have a glance at a few features to spot skew, outliers, and any weird spikes. So what we have done here is that for column in num underline column, we loop over the first 5 numeric features because 5 keeps it quick. Draw a histogram with 30 bars. Each bar counts how many rows fall in that value range, and add a clear title and axis here with plot.title so viewers know which features they are seeing. We plot it, render the plot, then move to the next feature. These histograms are important in our sanity check. So bell-shaped means well-behaved. Long right tail or many zeros means skewed, and the solution might be quantile transforms or log transforms maybe. Multiple peaks means mixed population, so model may learn useful splits. And sharp spikes means possible caps, floor, or data artifacts that need to be checked. The result here is that the distribution here for geochronology are clusters at a few ages. As you can see, treating them as numeric is fine. Booger are near Gaussian. Gravity at GM is right skewed, so our log or quantile and scale will stabilize it. We continue our sanity check by PCA plots and interpretations. So the first is import I bring in tools, imputers to fill gaps, quantile transformers to tame skew and outliers, scalar to balance units, PCA to compress to two-dimensional NumPy for array operation, and matplotlib to plot. Let's keep it fast. I cap to 1500 rows, so plots rendering instantly. X sub is a numeric features only. Y sub are the class label for coloring. Then we define a safe log transform. I make helper that clips negative to 0, then applies log1px equals log 1 plus x, and this compresses heavy right tails without breaking on small or negative numbers. Next step is preprocess. In a robust order, log compress first, fill missing with a median, map each feature to an approximately normal shape using quantiles, and finally standardize to mean 0, variance 1, so no features dominate. Next step is, and next line is the PCA to 2 dimensions. PCA finds 2 directions, PC1, PC2, that explain the most variance in this cleaned space, and Z holds the new 2-dimension coordinates. And finally, scatter plots colored by class. I plot PC1 versus PC2 and color points by the label so I can see any separation. This is the results. It's a broad overlap with mild trend. So I expected moderate separability. I think nonlinear models should do better than linear here, but it's acceptable, not great, but not bad. And these plots means some signal exists, but classes are not linearly separable in 2 principal components. I think it's normal for geology, but if PCA showed 1 cloud only, it means weak signal. And the fact is that if it shows near perfect split, that's likely leakage. So I think we are in between now. So I benchmark 4 learners on a stratified split using the identical preprocessing block. I rank by F1 to balance precision and recall, then confirm AUC is strong, and finally the top model moves forward. Here is the code block. We quickly compare a few models. We load train test split to make a train and a test set, metrics for accuracy, precision to recall F1, ROC, AUC, and pipeline to chain pre-processing with the model. For model, SVM with RBF, RandomForest, AdaBoost, LMP, and neural net. Talking about features and labels, X is a balanced training features, Y is a binary target. Now let's go to the model factory. I define mark CLF, which builds a pipeline, which means my preprocessor or preproc plus a classifier, and this guarantees the same cleaning and scaling for every model. In step 4, then in the model set, I created 4 candidate pipeline, SVM RBF with probability output, RandomForest with 300 trees, AdaBoost with 300 rounds, LMP with a small hidden layer, early stopping. We'll discuss it later. So the next step is train test split. I hold out 30% for testing. Stratify keeps class balance in both sets. Random stays 42 makes it reproducible. Then I loop over models for each fit on train, predict hard labels on test, and get probability for AUC. We prefer predict probability. If not available, use decision function. Otherwise, fall back to predictions cast to float. Compute, and finally compute metrics and store them. Finally, I build a result table, sort by F1, a balanced precision recall, and print with 3 decimals. What we do is to pick the top F1, check ROC AUC is also strong. If 2 are close, prefer the simpler or more stable model. This is a fast check, not a full cross-validation. This is our results. I pick RandomForest. It's based on F1 is 0.83 and AUC is 0.91. SVM RBF is close on AUC, but lower F1. MLP didn't converge at 300 iteration. Ignore or raise the cap. It doesn't matter now. We picked RandomForest. Now I log the preprocessing with the forest in one pipeline, feed it on the hold balance table, then save to disk. The file can score any new areas as long as the feature columns match. This is the code that build chains preprocessing. Impute, log1 quantile, normalize, scale, plus RandomForest classifier. And the fit function here learns on your balance sets. Then all the steps are fitted and stored inside the pipeline. And the last line is writing the fitted pipeline to disk. In the next stage, I reload the training pipeline, score every H3 cell, and convert probability into low, medium, and high scatter map. So in this code block, I loaded the fitted pipeline. I bring the train model back from disk. It includes pre-processing and the RandomForest. I select the same feature columns using the training for all cells. I predict scores and hard classes. I keep IDs and coordinates, then attach probability and class. Then I turn probability into low, medium, high using fixed threshold. 0 to 0, 0.33 or 0.33 to 0.66 and 0.66 to 1. And finally, I write a clean CSV for GIS sharing. It's a model's probability map bucketed in 3 bins. Blue is low, is less than 0.33. Orange is medium, between 33 or 66. And green is high. Orange or medium, and green is high. It's greater than 0.66. Cells in green are highest probability targets. Orange is halo moderate potential. And blue is background. So the pattern is that you can see the contiguous green belts inside larger orange zones suggest coherent signals, not random speckles. Edge speckle and isolated dots are common when binning per cell predictions. So please note that the highest probability target here means map cells with the highest model probability of our training class 1. So this is not a commodity such as gold or nickel specifically. The forest use all features you fed it. For example, radiometrics, gravity, seismic, lake geochemistry, geology, one hot. So the highest probability targets means places where that features patterns looks most like known positives in your labels. So here the labels for the training class actually mixes deposits and occurrences. The target is, so we can say that the training binary label here, the target is mineralization-like, not commodity specific. But you can also see which inputs or features drive your model. So we'll have a quick checks to verify quality. So there's also a good interpretable spread. So in center is median 0.21, means most cells low. The upper tail is 75% quantile of 0.5. That means only top 25% are greater than 0.5. The mean here is 0.29 with long tail, long right tail, means few high score clusters drive the green belt. 0 and 1s means typical, is a typical random forest probability, not calibrated. So you may want to use 10-15% high, use quantile cuts, and not a fixed 0.66. If you need calibrated scores, wrap our RandomForest with calibrated classifier CV. So now the goal here is to turn model probability into low, medium, high bins using quantiles. So I control how much area falls in each bin. I preview key percentiles of probability scores. For example, P80, P90, P95, P99. And these tell me what score marks the top 20%, 10%, 5%, and 1% of cells. I fetch two cut points, the 18s and 95s percentiles. Then I define three intervals, 0 to P80, which is low, 80 to 95, 95 medium, 95 to 1 high. And we avoid edges the edges that cause right at 1. The PD cut here assigns each cell to a label based on its probability and the bin edges. The result is a categorical column with values low, medium, and high. So I check the proportion of cells in each bin and expect 80% low, 15% medium, 5% high with the P80, P95 scheme. Quantile is a good approach because fixed bins like what we did, 0.33, 0.66 can over or underfill the high. But quantile bin guarantee that the map shows exactly the area share you want for your follow-up, for example, 5% high. So the results here is good. Quantile bins produce 80% low, 50% medium, 5% high, and that matches the P8095. And this is the plot, nothing specific to mention here. I also plotted it as a heat map and save is my favorite. One thing I would like to note here that this is map cells with the highest model probability of training class 1. And as far as I'm concerned, this is not gold or nickel. This is not commodity specific. The forest used all features we fed. And so the highest probability targets means places that the feature patterns look most like known positives in our labels. So here are labels. I said that the mixes of deposits and occurrences. And the target would be something mineralization-like, not commodity specific. So for the commodity specific targets, you need to build a binary label for each commodity. So maybe in another video I will explain how to build these binary labels. Then we need to retain the same pipeline and generate per commodity maps. This isolates drivers and lets you plan, for example, for gold or nickel campaigns independently while keeping a consistent workflow. Now you can hand off a clean CSV and a saved pipeline. In GIS, style the bins and overlay business layers. For reproducibility, pin seeds, note quantile cutoffs, and archive the notebook and model so the map can be regenerated exactly. So pretty straightforward. Keep the workflow simple and reproducible. Control leakage, balance classes, pick a solid model, then map bit quantile bins. Then you can go for validating against knowns. You may adjust selectivity and explain the drivers. And finally, swap targets to build commodity specified maps. If you find this video helpful, give it a like, leave a comment with questions, and don't forget to subscribe for more geoscience data tutorial.